This is going to be the first of a series of talks, kind of essentially being one big extended example to kind of highlight some of the work that that Zargham and I have been putting together on GDS. So you've seen GDS before. We've gone through and discussed things from a high level before and kind of described its implementation in the CAD/CAD framework. Within the context of the forthcoming work, what we're trying to do is really nail down the terminology and the definitions. There's an existence discussion looking about, like, when would you be able to say that a dynamical system can be represented within a GDS framework? We have conditions upon reachability, which will be one of the themes that we get to throughout the course of this example over the next couple of sessions. And this is really very easy to define as which states can be arrived at for a sequence of admissible actions, but getting the handle on what that means will take some, let's say, some world building. And finally, controllability, which is the issue of, well, given the fact that we would like to have some states that are reachable, what happens at those initial conditions? Because those initial conditions can often be things that we can set through governance or permute. And so understanding controllability of the system within that limited definition of what we call controllability is also something that's in that particular paper. Now, examples are always nice. We do have an example looking at the insurance market, but it's more is always better. And so the idea is to really put together for this series something that has more of a pedagogical flavor to it. So it's really more about expressing an environment that's perhaps a little bit more grounded in what we would immediately be able to understand as an example of a system, while at the same time hopefully sacrificing nothing in terms of what the predictive power is of the GDS representation is, and also being able to explore the consequences of reachability and controllability from within that context. So the motivating example here is about crossing the street. So what could be more simple than that, hopefully? We have a pedestrian who wants to cross a street. There's traffic on that street. And for simplicity, we just assume that there's an amount of traffic, which we would call Z, crossing on a one-way street. So it's just zooming by. There's a mechanism that exists in a community that the street is located in to provide a crosswalk, or if you're from the British English or continental European side, a zebra path or a zebra crossing at any point in the street. We're going to be fairly agnostic about what kind of mechanism and how that mechanism is implemented. We could have a centralized representative government, like a municipal board, making that decision, as in many, if not most cases. But there may be a decentralized activist group, concerned parents that need a crosswalk for children to get from one point to another for going to school, for example. Regardless of how that's done, we're going to sidestep the question of whether or not there are many different types of crosswalks and what kinds of attributes we can ascribe to crosswalks, and we're going to drill it down to a legally compliant thing that can apply to allow crossing over from one street to another. Now, the questions that you might ask here with regard to the system as a whole, which as taken as a whole, is a very high arching one. You're looking up and saying, well, all right, well, given the fact that we could build a crosswalk, should we build it? Should the crosswalk be built? Another question is, of course, and this is maybe the salient one for our example, is where along a particular street should a crosswalk? How should the crosswalk location decision be undertaken? This becomes a question for the governance process itself. How do people make decisions on the way in which they conform to and finally conclude upon some idea of where that crosswalk should be placed? And finally, things that are more mundane but equally important, who pays for the crosswalk and how is it funded and so on. So we're going to throw out a huge amount of very interesting questions. So one of the things we're going to throw away is the debate on whether or not a crosswalk should be built, how that implementation happens. We throw it away with a caveat that, in a way, that question, how do you decide, actually has a lot of bearing when you're actually thinking about how to think about the system. And so if you're thinking about a GDS representation, it does stand to reason that you would maybe want to have that discussion of how do we arrive at a decision coming after the representation has been formed. It is not the way the real world works. The real world works with everybody having their own mental model. But in our environment, we're just going to assume that a collective or a representative government has said, yes, a crosswalk should be built. And the operative question from their point of view is, where should the crosswalk be built? And so we have to tease out then the circumstances under which that crosswalk is going to be provided. We have to understand the road. We have to understand individuals in that system. And so what I'll do now is walk through kind of one particular way of looking very simply at this problem confounding for the moment things that we don't necessarily have good understanding of from the point of view of stepping outside. Things like, for example, the preferences or the decisions or what it is that individuals would like to do, their mental models of their own on why they're crossing the street. We're going to put a little bit of layering on that just to facilitate our grounding of this assumption as a dynamical system. But then we're going to see how GDS separates out different components of the system in between things that change over time and things that people can choose to do. So bearing that in mind, let's start the crosswalk problem. So we've got a road, it's of indeterminate length at the moment. And on this road, there are merchants or commercial properties or something else that individuals would like to go to. So let's pick as an example, a representative example of why would anybody cross the road. It's not going to be a chicken issue. I thought about the chicken joke. I decided against the chicken joke. In the end, it's your friendly local gaming store. So your friendly local game store has got, it's got everything, right? It's got Warhammer, it's got Pathfinder D&D, it's even got, Witcher die with coin, it's got resin miniatures, it's got everything you would ever want to have. But the problem is, of course, that it's separated from you by a one-way street. So you've got traffic going across this environment, and you as the individual would like to make that particular trek across the street, and you want to do so in such a way that minimizes some criteria. Now, here's where the behavioral assumptions are, that we're using this to fix our intuition, but we're not going to be conditioning upon that in the GDS representation. Instead, we're going to use this as sort of a method of teasing out reasonableness with regard to what we think people might later on be able to do. And it actually becomes important when we're looking at things like equilibria that we expect to see. So one assumption we can make is that, well, given the fact that you would like to kind of be right across the street from where you want to go, that there's some ideal point that a pedestrian would like to cross the street at. And it's different for every pedestrian depending upon where they're trying to go. They're not all trying to go to the store, they're all trying to go to different locations. But conditional upon where they would like to go, deviations from their ideal point cost in some sense more, either in terms of time, in terms of effort, or just the idea that is supported by survey data that people just say, look, I just want to get there. And so without even articulating it, they just want to go in a particular direction. Now enters the question of where we're going to place this crosswalk. So if we put the crosswalk in a particular location and say, this is where you are going to cross, then individuals immediately condition upon their behavior. If I use that crosswalk, well, that means that instead of crossing directly, I'm taking a different path. And that difference in path leads to different behaviors. Now, again, we're not going to assume anything about how individual preferences are formed in that context. Instead, what we're going to do is say there exists some mechanism by which individuals observe their surroundings, which includes the location of the crosswalk, and then they do something that they're allowed to do. And the characterization of what they're allowed to do impacts the system as a whole, as we define it, becomes the purview of separating out between what individual admissible actions exist and what the system transitions from one state to another conditional upon that. Now, you might expect that, for example, an individual could say, well, forget the crosswalk. That's something that they're allowed to do. They can say, well, hey, I can just cross wherever. And then you can think of different things that might occur that you need to keep track of if you're looking at a system moving from one particular state to the next. So in one particular state, they're crossing the street, they have good luck. They make it past just in time. They're home free, they're safe. Traffic continues as always. On the other hand, maybe they cross the street, but they're fairly slow. They still have some fairly good luck because what happens is that they stop traffic. And so the guy driving is not particularly happy about this, but the individual crosses safely to the other side. And finally, maybe they're getting across the street, but something happens, they trip, they fall, they didn't see somebody turning from a corner, and a suboptimal outcome for probably everybody. So these are the types of things that can occur conditional upon the behavior that's happening. And whether or not that behavior is something that is injected into the system from a behavioral model is something that we slowly move ourselves away from. So keep it as a mental model. People are trying to choose where to go, and why wouldn't everybody just choose crossing at the crosswalk? Well, there are some incentives that they are conditioning on that make them take the risk to cross somewhere else. Okay. What we want to do now is take that whole narrative and actually build a dynamical system from it, such that we have consistency in what is chosen by external influences and how they change the system. And we start with the state space. And the reason for this, if you remember from the definition of GDS, GDS is itself an internally consistent state space approach to incorporating external interfaces in a state transition process. Now, that's a mouthful, right? But what we're doing is teasing apart the idea of what is the system, and we're casting that into, well, what's the sufficient statistic that I should be looking at that says, what's the system at a particular point in time? So if your takeaway from the state space is, that's all I need to know to get a snapshot of what the system is at this point in time, that's why a state space representation is so useful. There are other representations that you can use for a dynamical system, but in the GDS framework, being able to say that this is the way the system is right now allows you naturally then to ask the question of, oh, but how does that change over time? What happens next? So for the example that we're creating, let's use one particular representation of a state as the traffic flow, the change in the traffic, say number of cars, for example, or amount of kilograms of weight per time interval. It's got both a magnitude and a direction, as we know, because it's in a one-way street. We would expect most of the time, for example, to be going in that direction, but traffic could stop. So we have magnitude and direction that's setting in the system. Okay. Now, not every single environment is going to admit a single point for the state space. State spaces can be incredibly rich. The more complex the system is, the more complex the object is. And one of the outcomes of the paper itself is, in fact, to describe it pretty close to the full generality of what it is that you can call a state and how that state can change over time before you start overloading or burdening the ability to create something that changes. And the definition itself of what does it mean to change can become overloaded. But in this particular situation, we're saying this is sufficient. We're going to say that the flow of the street is important enough to all stakeholders that they take that as the way that the system is operating at this point in time. Now, let's look at this state space in a little bit more detail and start carving out places that might be interesting. And I use points of interest to describe interesting locations, with points is in quotes because it isn't actually points per se. So I don't want to I want to disambiguate that and just say POI as the idea of where is a place that's nice to look at, but they aren't necessarily single points. And let's define then the state space as an interval between minus C bar and C bar, where C bar, which is a positive number, is the maximum traffic flow. You might be asking yourself at this point, well, if it's a one-way street always going this way, why do we look at negative values? Why would traffic ever go the opposite direction? And the reason is we're going to make an assumption about the partition of the set of these particular traffic flows to lend us a signal on when an accident has occurred, when somebody has crossed the road and something has happened. It's simply an assumption on extrapolating something about the state of the system as representative of what's occurred. It's not the only way to do that, of course. You can actually have people calling an emergency telephone number, calling 911 in the States, and that would be your representative signal, for example. So points of interest in the state space include things like no flow. Suppose that nothing is changing and moving over time, a traffic jam has occurred, and you might even ascribe preferences for stakeholders on whether or not that's something that they would prefer to have or not have in that particular part of town. On the other hand, you may have a constant flow, it's just equal to C, a positive number, and then you might have rankings between different positive numbers where high flow maybe is preferred to low flow. You want to keep the traffic going because perhaps there's a dependency or several dependencies in the entire logistics of the transport system within that area. If X is less than 0, traffic is basically being turned around and going the opposite direction. The interpretation we're ladening here, and it's just for the example, is that there has been an accident, and so traffic is being routed in the opposite direction. They get to a point, they turn around, and you count the flow going the other way. And this is something that we would expect stakeholders to avoid. And just to give a little bit more richness to the characterization of such a set, we also have the chance of seeing if we sample in a particular way. We've been kind of fast and loose over time, but remember in GDS, you can do a lot of really nifty things with time. And one of them is to scale back up and say, well, let's look at time every day. seems like every morning there's a traffic jam, and then every afternoon traffic seems to be flowing at this rate, and every evening there's a traffic jam. So you'd see periodicity over time. And then the points of interest are the different points that are the periodicity is showing us that we're getting repeatable, like stop-go traffic over the course of the day. Now, all of those things are restrictions of the broader state space to subsets. And eventually, this is what we're going to get for reachability, the places that are reachable for different types of actions that are being taken by individuals that interface with the system. But for now, it's nice to think about them as their characterizations. So just a little bit of the ability to kind of tease out the dimensions of each of these sets is going to be helpful for us later on. For example, if you have stopped traffic or constant traffic, even though constant traffic is a flow that's always moving, it's being represented by a single constant number. Each of those subsets is a single point. But the accident one, where traffic flows in the opposite direction, is a subset consisting essentially of half of the state space, everything from minus c bar up to, but not including 0. So you have a one-dimensional line interval. And finally, the points where we have this periodicity, well, if it's in discrete time, you have a finite number of points before these points repeat themselves. While in the continuous time, you have an interval of uncountable points up to, but not including the point where x0 is equal to x capital T. And this is a subset consisting of a discrete or continuous collection of points. These are the unique values for the traffic flow. And so you see, as you are looking at the different kinds of phenomena that are interesting, you start to build richer and richer characterizations of the sets of points that you care about, quote unquote, from a stakeholder's perspective. Being able to reach, for example, that single point of constant flow with some degree of confidence, with some probability measure, or most of the time, becomes really, really important when you're placing a crosswalk. You don't want to place the crosswalk in a position where you end up with essentially a traffic jam most of the time, if your preferences are to have flow going. Well, that means that you have to have, conditional upon the placement of this crosswalk, the reachable state being that single point. So we have essentially a triumvirate of 3 different concepts that we need to build for a GDS framework. The first one, as mentioned, is the state space. The second one, though, is this pedestrian. The pedestrian is interacting in a way into the system. They're interacting with what's happening with the traffic flow, but they're doing so by selecting things that the traffic flow doesn't really care about, that they're looking in this particular case for where to cross the street. So we think again about that line of the street itself, and we say, well, okay, let's consider this as, individuals choosing from a menu of places that they can cross. And at this point, it might occur to you, you could say, well, hey, why don't I go back and change my system state located, the idea of what the state space is, to include just points on the line, and then I can include where the cars are, and then I can include the flow at the same time, and call all of that the state. And this is where GDS kind of provides this very, very strong semantic distinction. Because what you're doing is, as Zargham would say, you're putting the procedural automation of what the state does as it changes over time, conditional upon what people do, in its own right, as separate from the decision automation of what individuals do when they make their decisions conditional upon what they see. These two are completely separated in a GDS framework. And so although you could certainly model a system where it confounds the decision-making with the state space, it's less useful in this context. It's less useful because you cannot then disentangle the external influences that are affecting how the system changes given by that state space, or that state, the system's state, how that changes over time. And this is important because we're going to figure out almost toward the end of this, how it is that the crosswalk decision is placed into this context. And so keeping these things separate is important. So let's consider this input space in more detail. Let's let the line now, just for simplicity's sake, be finite. So it's actually a city block that you're trying to cross over. And one representation could be a line that stretches from minus cap L to cap L. So we say it's a length of 2L, and we have put a 0 point in the middle, which is just to give us a normalization, in fact, in what happens. And we can think that, hey, well, the admissible action, the thing that someone is allowed to choose, could be some part of this street, the location that they can actually walk to. The simplest one, of course, would be to say, well, they can choose anything along that street. They can just step off the curb and walk across the street. But bipedal mobility is an assumption. What about wheeled mobility? What happens in that case? Well, in that case, there may be certain parts of the street that you can't cross. There are only areas that you actually have the grade, which is able for you to be able to move in a wheeled conveyance from one point to the other. And so then the admissible action set becomes different for that individual. So you have to take the different locations, which may be separated from each other on the line, and take the union of those and say, that's what that individual has as their available action for crossing the street. And notice also one thing to be very clear, when an individual is deciding whether or not to cross a street, still standing there not crossing the street is an admissible action. So this is a callback to some of the commentary from Matt Stevenson back when we were first describing admissibility and action sets. Just walking away from the game is an admissible action. So part of the admissible action has to be the decision on whether or not to cross. And you can finagle that a lot. You can actually try to highlight a particular part of an admissible action set, like, for example, choosing anything along this line, but we're also going to attach minus infinity. And if you choose minus infinity, that means you're not crossing. But in a sense, that's kind of breaking the separation between what it is you're doing conditional upon crossing or not crossing. And so it's quite nice to keep this as a separate space on its own. We're going to staple these spaces together, but let's have that as a decision in its own right. So let's set up capital S as simply consisting of a 0 and a 1, the 0 meaning you don't cross, and a 1 meaning that you cross. Notice also that just in the way that we're looking at the impact of being able to cross, that the state itself, remember this is the traffic flow, could have an impact on what you can choose in terms of where to cross. For example, if you had constant traffic flow, but very, very high traffic flow, maybe that actually removes the points at which you can cross. Think instead of a street of a river, and the river itself has risen. There's a huge flow because of a flood, and a ford where you could have crossed before is no longer available. So now you have state dependence on the admissible action that you can take. Another way to look at that also from our context of a car accident or an accident between a pedestrian and a car is that in the time that you have an accident itself, maybe every single point has been removed from consideration for following pedestrians that are coming along. That they come by and the police say, hey, sorry, this is all off limits, there's an accident. Now you can't select any of these things. And that's conditional upon the current state where traffic is being redirected and moved elsewhere. So that dependence is an important thing to remember for the individual in admissible input set. So let's say that this is dependent upon the state at time t, and that at time t, the individual looks at the state xt and decides from their available actions, their admissible actions, let's call it u, which depends upon xt. And let's just concatenate, let's assume for the moment bipedal mobility, they can choose any point on the line PL, they can choose that point and to cross, and they can choose whether or not to cross in S. And so U sub xt, that set, the admissible input set, or the admissible action set for the individual, is equal to the product of your choice on where to go and whether or not to cross. And now I'm going to introduce something to think about, because it's important to think about the directions in which you can expand the notion of who is actually interacting in the system, and then I'm going to throw it away. So let me introduce the idea of having an arrival process where certain numbers of people are arriving simultaneously at a particular point in time. Let's say n sub t pedestrians arrive at a particular point in time. Well, they're all allowed to cross the street. There may be collisions where people try to cross at the same point, but people are pretty good about avoiding each other. But that does mean that you have as an admissible action a vector being drawn from each of these admissible action sets. And notice that although I haven't written it that way just to ensure that we keep kind of the notation a little bit clean, it could even be, of course, that the admissible action set is different for different people. As we were seeing for bipedal mobility versus wheel mobility, those admissible action sets could be different from each other. Okay, now having introduced the baby, out it goes with the bath. For parsimony, we're just going to say, hey, there's one pedestrian, has the same admissible action set and what follows because there's nobody else. So we're just going to set that n sub t equal to 1 and what follows. That also makes the equilibrium analysis a lot cleaner, but remember in the background, what you're thinking about when you're putting a single crosswalk in place is actually pedestrian flow as well as traffic flow. Okay, and finally, we've got this pedestrian that's been moving around, but remember we were discussing the notion in that beginning motivating example of whether or not they cross the street successfully. We kind of left it vague as to whether they make it across in time or fall prey to traffic, either traffic being stopped or actually ending up in a position where they're getting into an accident. There's something else going on. And that something else going on is an external influence that we assume is not really a part of the decision on where to cross the street, but rather a reflection of the circumstances under which something might happen. And by might happen, we say, well, there's an element of randomness here. That you cross the street, we don't really assume that people are lemminging themselves into the street where they kind of run into the street and then bonk into the cars because they don't see the cars. It's more that they've just misjudged the situation, or that something happens, that they trip and they fall, for example, which is not a deliberate action, but it's something that occurred. That randomness we're going to encapsulate in luck. We're going to call the set of things that you can choose that are lucky or unlucky is just a shamrock. And it also happens to be 0 or 1. It's just to separate it out from the decision space S. Good luck, L equals 1, means a pedestrian has a higher chance of crossing the street successfully, conditional upon deciding whether or not to cross. Bad luck, L equals 0, means a pedestrian has a higher chance of crossing unsuccessfully. And so now we've expanded, notice, what is being interfaced into the system. What is coming into the system is now where you cross, whether you cross, and then this element of luck. And so the admissible input to the system is now being drawn from this product space of feasibility, S, and shamrock. And you have a vector that is inserted into the system. And notice, we don't possibly ever have the ability to measure or to observe luck. So observability becomes a key component of this, because if we can't observe luck, we need to model it. And we need to figure out, well, how would we figure out whether someone is lucky or unlucky, and how would we do this? Would we back this out from the data? Would we generate our own models of luck or being lucky or unlucky? These are all considerations when we know it's coming in and impacting the decision, or rather the outcome, but we do not know the actual value of someone's luck when they step up right before they decide to cross the street. So this is the characterization of the admissible input space and selections from that space. These are things that anybody can choose, any of the things within those, up to the dependence upon the particular state at that point in time. Okay, so we've reached 2 out of the 3 of the triumvirate. The third one is conditional upon the fact that we're using a particular metric or a particular sufficient statistic for the state, and we have influences coming in. How does the state move? What happens? How does it change from one point to another, given the fact that we actually have this external influence and these admissible actions coming in? That transition process from the current to the future state, given the admissible inputs, is how the system moves over time. And remember, the system, the transition itself, has to be able to accept any action from the admissible input set for any of the states that it can reach. So that's why the system itself, when you engineer a system and design a system, that the behavioral assumptions, if you impose them, are critical, because you may be cutting out massive swaths of what's admissible by saying people will do that. And sometimes that's incredibly dangerous, because you don't necessarily know if they do that. And even if they want to do that, maybe they make a mistake, or maybe somebody else comes along who doesn't want to do that. So making sure that you understand what is available, and then ensuring that you know how things change, provides the power of something like a GDS framework, because you still get some results about what might happen versus what might not happen. So state transition may be represented by a function. We're going to see in a moment how it's represented by a matrix. Simple to write down as a function, saying that tomorrow's state is some function of today's state, the admissible input, and then some parameters. I'm going to call those parameters, and leave it very vague at the moment right here, some parameters K. Those K parameters influence the system somehow. Why would we do this? why do we parameterize a state transition function? What will we use to connect this to the system? The system is a system. Well, the reason is because of the whole problem that we started out with, which is the crosswalk problem. The mechanism design problem that we are facing is inextricably intertwined with the governance surface of the system. And you need that injection then of the parameter that's being chosen to move from a class of mechanisms, crosswalk somewhere, to an instance of that crosswalk location, that point K inside PL that we're building and investing in the crosswalk to be selected. And that selection, of course, is happening from governance. Now, it's true that in time, that governance parameter may be updated. They may come over and just sort of, tarmac over, asphalt over one crosswalk in favor of moving it to a different location. They may upgrade the crosswalk with LEDs to have it available and visible both at night and during day, and so on. But it's important that regardless of which of these is occurring, as long as there is the state representation of traffic flow, the state transition from different points in the state space will depend upon that parameter value K. And that's where the design comes in. When we're designing the parameters or the classes of parameters, oftentimes when we're working with clients, we're stopping at the classes and then saying, hey, if you want to know an instance from that class, let's build a CAD model and do parameter selection under uncertainty so that we grab ourselves some parameters. Then we can insert those in. Depends upon what they're looking for and the degree of generality that they're asking for. It also depends upon the criteria that eventually the governance process uses to assess different crosswalk locations. That's something that we're going to get to in the following sessions. Okay. Having said that, and having brought on board this notion that we have a state transition that depends upon the current state, the admissible actions, and a set of parameters, let's look at a very simple partition of the state space and transitions from one regime in the state space to another. This is like hopping from different points of admissibility to other different points of admissibility. And there may be absorbing states, then there may be states for which you never reach. In this very simple case, let's suppose that you went out to a street and just, there's a crosswalk present, you see the crosswalk, you sit there without knowing anything else about the mechanisms, you just start writing down what happens. And you say, oh, this time we had an accident. Next tick of the clock, oh yeah, and then the traffic was stopped. Next tick of the clock, traffic was still stopped. Oh yeah, now traffic is going. And you're writing down the relative frequency of the transitions between different types of realizations of traffic flow. If you did that without knowing anything, what you'd end up with is a series of probabilities that are in the Markov decision process, a Markov process for the transition matrix. So here's a very simple example of partitioning out the state space into 3 different locations. Less than 0, an accident has occurred, equal to 0, where traffic is stopped, and then greater than 0. Traffic is moving without saying whether it's constant, whether it's variable. And what we're looking at in this environment for the simple case would say to, if we were just not looking at the GDS environment, we're just looking at the way the probabilities would stack up, what would we be seeing? And here I've just inserted some numbers that would be the thing that was seen for this particular idea as a motivating example of what you would do from a data-driven process. So for example, in that first column, we would say, well, if there was an accident, x sub t is less than 0 in period t, there's a 50-50 chance that you're still in an accident state in t plus 1. That's the second column of xt plus 1, less than 0, first row. Or traffic goes from being moved away to being stopped before the police then let traffic through. That's a probability 1/2, but you don't go from accident to traffic going through ever. So that probability is 0. And remember that each of these rows has to add up to 1 because you're conditioning upon a particular starting point in the state space. And that second row, for example, where traffic has stopped, 20% chance that maybe there's an accident, somebody trips and hits their head on your car while the car is actually stopped because you aren't at the crosswalk, perhaps. 50% chance that you're still stuck there a little bit later because this seems to be a place where congestion occurs, or a 30% chance the traffic goes, so start-go traffic. And finally, you have traffic is flowing. There is perhaps a 10% chance of an immediate accident where something happens, but then you may get into a traffic jam 30% of the time, or with 60% chance, traffic continues to flow. So this is, without knowing the inners of what is affecting these transitions, a way of looking at from the outside a reduced form of the transition that you're seeing from xt to xt plus 1. And that in the paper is the h function, just looking at the reduced form without looking at the internals, or to put it differently, thinking of all the external influences as simply being a part of the system's box and just looking at what's going in as xt and what's coming out as xt plus 1. But of course, as a final piece of the representation, we want to be more than that. We want to be able to have that ability to look at that admissible action vector coming in and the states and say, what happens next? So one example, again, just an example environment of such a Markov process, now with what agents, what pedestrians in this case are doing, is this one. And what I'll do is I'll go through the first two rows and leave kind of the third row as a homework assignment. As something to think about, it's not a big deal at all. The first row is exactly the same as before. We kind of think about an accident situation as sort of being outside of the pedestrian's interaction because the pedestrian is on the ground. So this is more about ambulance services and the efficiencies that come out of helping rectify the situation. That second row is the traffic has stopped in the current period. What happens next? Each of these three items that occur for what happens in the future, of course, have to add up to 1. And you can see that you'll be able to see that they do. Let's take apart that first one. That first one has a product of 3 terms. One of those terms is whether or not to cross the street when traffic is stopped, S being 0 or 1. If you don't cross the street, we assume that the probability of an accident is 0. So you are not the one causing an accident, you're not crossing the street. So S equals 0, that product equals 0. So we say S is equal to 1 for the moment. On the other side, we have good luck or bad luck. We have L. If you have, for example, good luck, then regardless of whether or not you cross the street, if you choose to cross the street, wherever you choose to cross the street, you have good luck and you cross the street. That's maybe because people are sort of attentive as they're stopped and maybe they see you crossing. In a good luck environment, you cross the street safely and there's no accident. Let's suppose you have bad luck. So a bad luck outcome, L is equal to 0, 1 minus L is equal to 1. Now, here you are, you're at the crosswalk and you decide to cross. You select point P equal to K, the location of the crosswalk. You're there. As you're walking across the street, you face plant, whack. Annoying, but not an accident. You brush yourself off, you kind of, wave to the drivers, you walk on, and then you jump into D&D 5e to kind of soothe your wounds. No problem. P is equal to K, that middle term is equal to 0. If you choose to go somewhere else, P is not equal to K, and now you've got a positive mass for a probability of getting into an accident. And this would happen in this idea of kind of like I'm weaving around cars. Cars aren't really expecting pedestrians in the middle of a traffic jam. Some guy is just lifting his foot off the brake just to move his car closer to the car in front of him, hits you, or you trip, or you fall, and you have an accident. And in this, there's an artifact here. I've normalized it so we have nice probabilities by dividing by the length of the interval, but that also kind of implies that the further away from the crosswalk you are, the more likely it is that you're going to have an accident. May or may not be justified by the attentiveness of a driver in a traffic jam being close to a crosswalk and expecting people or not, but it's an artifact. It's really just there to normalize that P minus K to ensure that we're within that probability. And so that's a transition from traffic jam to accident that fully incorporates the admissible actions in the state transition. So the state transition depends upon this, and notice it also depends upon K, that parameter. That crosswalk location is part and parcel of this. Now on the flip side, you could have a traffic jam still being a traffic jam because of the fact that you cross the street, and that's what that middle cell is showing. You'll notice that the term inside the parentheses next to the S is just 1 minus the term of the other side, and that's deliberate. That basically says that conditional upon crossing, when S equals 1, there's a chance that in the act of crossing, you cause the traffic jam to continue. And that's all that probability is. The probabilities have to be the same in the sense that they have to be able to add up to a particular number such that the third cell is 1 minus that number. In this simple example, those two numbers are the same, so that when you add up that number plus 1 minus that number multiplied by S, you get 1 times S. So going from stopped traffic to traffic moving happens with probability 1 if you choose not to cross. Otherwise, it doesn't happen at all because there's a chance of having either continued stop traffic or an accident. And so this is how we're building this transition function. It's that F function, but we're building it in a matrix form because it has that dependence on the state. That's that column where we say what xt is. And it has the impact of what the pedestrian is doing. That's the P, the little s, and the little l, the script L. And then it has parameters. One of them is a structural parameter, capital L, the length of the street, while the other is a governance parameter, and that's K, the decision on where to place the crosswalk. And I'll leave for you as an exercise to go through that final row where traffic is moving. And now what happens when traffic is moving? Do we get an accident? Do we have stop traffic, or do we have traffic continuing to move? Those are the three pieces of the triumvirate. We've actually completed the GDS representation.